Okay, so section 5.3, we're going to focus first on conditional probability. We'll focus on the independence part later. So first you need to know what is conditional probability. For most of the probabilities that we've been dealing with so far, they've only really been based on one event or mutually exclusive events happening. Here, instead, we need to start focusing on when two events happen, but the second event only happens because the first event also happened. So conditional probability is the probability that one event happens given that another event is already known to have happened. So we're going to start using some new notation that you have to get familiar with. And here I have it underlined where it's probability of event B given that event A has already happened, or under the condition that. So your new symbol is basically just a vertical line. Almost think of it as like one of your little absolute value sides. Usually you just make it a little longer than your letters for what your probability of your events are going to be. Okay, order matters when we're talking about conditional probability questions. Just like with division and subtraction, here I have an example that 10 divided by 2, which is 5, is not the same as 2 divided by 10, which is 1/5. Also think about when you have 5 minus 3, it's not the same as saying 3 minus 5. So when we start looking at examples on the next screen, you're going to see what exactly that means, where the event order does matter with how you're writing it. Okay, so on the next screen, let's jump right into an example for conditional probability, where here you're going to be given two-way tables, and you may not need all of the information in the two-way tables. For the most part, we have been using the totals or different pieces here inside. So each question is going to determine which one you want to have, and you may want to isolate either the rows or the columns for yourself so that you're only dealing with the information that we care about. So if we know that a person owns a home, what is the probability that the person is also a high school graduate? So we're starting with that they're a homeowner. That's our first event. Now we also want to think about what is the probability that they're also a high school graduate. So we want to now focus on this high school graduate piece, but we only care about this row of information all the way going across. We want to find out when is it that both of these events happen with each other. Okay, so here we would say that we have 340 homeowners, that's what we're starting with, and we're wondering how many of them are also high school graduates, which is 221. So you have the probability that you have a high school graduate is given also that they own a home. So you have 221 over 340, which is 65%. Now, I know some of you don't want to write out all of these words, but you really need to do that piece. Your only other your option here is you can get rid of the word given and you can put the new symbol in, but you need to have the words written somewhere. If you don't want to write them there out in a long way that way, you actually have to define your events. So if we go along with defining our events, you can use the short notation. So if you told me, for example, that event A was that they own a home and B is that they're a high school graduate, you can write it out in the short notation so that you would have the probability of event B given that event A is the 221 divided by 340, which is 65%. Okay, so you just have to make sure that you're actually giving all of that information when you're doing it. You can't just put the event A and the B without having defined it first. So similar to question 1, if we know that a person is a high school graduate, what is the probability that the person also owns a home? So why don't you try this problem, pause the video so that you can now try the problem. And write out what you think it's going to be. So we know that a person is a high school graduate, so we're focusing on the high school graduate column. What is the probability that a person owns a home? So we're saying basically that we care about the total of 310 people, and we only care about the 221 that actually own a home. So when we're writing out our response, we would say that the probability that a person owns a home, given is also a high school graduate, we would say we have the 221 over 310, which is about 71%. Now, if you wanted to write it out in the short notation, because we also have A and B defined, you could say the probability of event A given event B is 221 over 310, which is also 71%. So even though we're still using the same events, the order is different, so we're getting different percentages because we're talking about different pieces. of the information. So let's try another example, or let's look actually at the formula where we have the the conditional probability formula. So we found this actually on your reference sheet, where you can have the probability of event A given event B is actually the probability of event A with the intersection of B, or the probability of event A and B, over the probability of B. Now you can go into your textbook and look onto page 319 to see exactly how this formula is derived, and we can go over it in class if you have questions about how that came about. So let's try this one. Pause your video and go through. So we have phone usage. See if you can figure out the answer to what is the probability that a randomly selected household with a landline also has a cell phone. Be sure you write down your calculations. Okay, so hopefully you've gone through and you've done your work. Remember, just show your work. Don't just put the answers down, because you're not going to get full credit on a short response, on a free response question on the AP test. So you can have either two different options here for showing your response. We have the probability of a cell phone given a landline. So we have the cell phone is 0.51 from here. We're focusing, remember, on that we already know that we have a landline. So we have this first row of our table going across. So we have the landline, cell phone is 0.51, the total is 0.60. You do all the division, you get 0.85. Or you can apply the conditional probability formula, where you have the probability of having a cell phone and a landline is being 0.51, which is here in our table, over the probability of having a landline, which is 0.60. Again, same formula, just different ways to write out your notation. So we can say there is a 0.85 probability that a landline user also has a cell phone. You could change it to a percent if you prefer a percent, but just so that you know that sometimes they stick with, since we already had our numbers here in the table as decimals, that we might write it as a decimal. So right now, pause the video and go try and do the check your understanding problems that are in this section found on page 321 of your textbook. And when you're done, check your answers and come back to the rest of this video. Okay, there is another rule that you will also need to know. It's called the general multiplication rule, so that we're going to focus on that. How do you find the probability that both events actually happen? So the probability of A and B. So we want to use the general multiplication rule. This rule is not found on your reference sheet, but you can check on page 321 of your textbook to see how it is derived. They go step by step, and I can answer your questions as to how it came about in class when we have class. So your general multiplication rule is you have the probability of A and B, which, remember, is also the probability of the intersection of A and B. So here you're going to take the probability of A and multiply it times the probability of your conditional event, your conditional probability, which we were just practicing. So remember, probability of your event B given event A is considered the conditional probability. So playing in the NCAA, you would have about 55% of high school students participate in a school athletic team at some level, and about 5% of these athletes go on to play on a college team in the NCAA. So we're talking about 5% of the 55% of high school students. So what percent of high school students play a sport in high school and go on to play in the NCAA? So taking the general multiplication rule into account, we would find first, we have to find the probability of the first event that they play a high school sport. Well, we're told that in the problem, 55%. We also have to find the probability of playing in the NCAA, and given that they are also playing a high school sport, which is 5% or 0.05. So now, applying the general multiplication rule, you're just going to multiply these two numbers so that instead you have the probability of a high school sport and the NCAA sport would be the notation to write out, or you could write the probability of the high school sport times the probability of being an NCAA sport athlete, given they're also a high school sport. And play a high school sport, you have 0.55 times 0.05, which gives you 0.0275. So our statement would be about 3% of high school students will play a sport in high school and in the NCAA. So simple little multiplication steps that you can do. Your book also has some other examples of how to do this part. The other method you can take is using a tree diagram. So a tree diagram basically is really only useful when you're starting to have to think of a sequence of events, a sequence of outcomes happens. And it's a good graphical way for you to see, and some of you are going to like using the tree diagrams and some of you may not as much. So let's say that we have a girl, Shannon. She hits her snooze bar alarm clock, and sometimes she hits snooze, sometimes she doesn't, and it gives you the percentages of where. So if we go through, we can say we take this whole event, her alarm goes off, and she's either going to hit snooze or she doesn't hit snooze. In the problem, they say that she hits the snooze bar 60% of her days. So we can draw that here where we write 0.60 in with our tree diagram. Now, I already have the tree diagram created just to save some time so that you can see how it works. So if 60% of the time she hits snooze, 40% of the time she doesn't hit snooze. Okay, then it says if she doesn't hit snooze bar, there is a 90% probability that she makes it to class on time. So here we have that she's going to end up, if she doesn't hit the snooze bar, there is a 90% probability that she makes it to class on time, so that's down here. So she doesn't hit the snooze bar, so that's 0.90, so then she must be late if she doesn't hit snooze 10% of the time. However, if she hits the snooze bar here, so she hits the snooze bar, there is only a 0.70 probability that she makes it to class on time. So this is going to be 0.70, so the remaining must be 30% of the time, or 0.30. On a randomly chosen day, what is the probability that she is late for class? So we have to think about, okay, each one I go through, the probability of that she hits snooze and is on time is actually 0.60 times 0.70, which is 0.42. And over here you can pause this and you can see how I came up with each one of these individual probabilities for what our graphic looks like. Okay, so what we have to go down here and we have to see, oops, sorry, let me make this a little bigger. Sorry. The probability that she hits snooze and is late is about 0.18. So we get that here from our probability from above. The probability that she doesn't hit snooze and is not on time or is late is 0.04. So we're looking at two pieces here. We're looking at this one and we're looking at this one because those are when she's late. Because they are mutually exclusive events, remember we can use the addition rule that we learned in the last section for those, which means the probability of her being late is 0.18 plus 0.04, which is 0.22. So she is not on time or is late to school about 22% of school days. Okay. Now, that's just one way you could go about solving it. You could draw the table out. Some people like to do it as a table method, but in certain situations, a tree diagram is actually a little more useful for you. Okay, so suppose that Shannon is late for school. What is the probability that she hit the snooze bar that morning? So we could use, again, the conditional probability formula in order to do that, using the information from the previous set, where we have the probability that she hits snooze given she's late for school. Okay, so instead of working the other way, we're saying that she's already being late, and now we want to know, did she hit snooze? So the probability she hits snooze and is late for school over the probability that she's late for school, we would have here 0.18 over 0.18 plus 0.04, because she's actually late for school in two different types, equals 0.18 over 0.22, and we get 0.818. So when Shannon is late, there is a 0.818 probability that she hit the snooze bar that morning. Okay, so again, you're still using the conditional probability formula throughout when you're doing it. It just can look a little different with how we're using it. So I want you to try this problem, and I want you to come in, I want you to answer questions A, B, and C here. So I want you to come in with a tree diagram, find the probability that this person describes his or her grades as good, and given that this person describes his or her grades as good, what is the probability that she or he is a heavy user of media? So give it a try, just do it in your notebooks. We'll go over it in class when we have class next. If you have any questions on anything, please feel free to email me.